So for 3D, this is sigma is equal to d epsilon, which we got in the previous class. Sigma x, sigma y, sigma z, tau xy, tau yz, tau xz is the stress matrix, and epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, and gamma xz is the strain matrix. And you got the constitutive matrix, which is D, which is 6 by 6 matrix. Order of the matrix is order of 6, square matrix of order 6. And for 2D, if you consider a simple plane like this xy, then you have two normal stresses, one in x direction, that is sigma x, and in y direction, that is sigma y. And along with that, you also have, because I consider this as a plane, you also have shear stress in this xy plane, tau xy. So sigma is equal to sigma x, sigma y, tau xy. Similarly, what is epsilon? Epsilon then, epsilon is equal to epsilon x corresponding to the sigma x and sigma y. You have normal strains, that is epsilon x and epsilon y, and shear strain, which is gamma xy, right? Gamma xy. So you in the previous class we have also discussed that for 2D, just like 3D, you'll get sigma is equal to d into epsilon. And just now we have seen sigma is sigma x, sigma y, tau xy, which is, or I'll write here, sigma x, sigma y, tau xy is equal to some matrix into what is epsilon? Epsilon x, epsilon y, gamma xy, right? Okay, fine. So you will get some matrix. We get some matrix. Now we know this order. Can you able to look into the video? Okay, fine. Just a second. Okay, so you will have some matrix into epsilon x, epsilon y, gamma xy, and now you know the stress matrix order is 3 by 1 for 2 dimensions. Similarly, for strain matrix is also 3 by 1. And what is this order? What is the order of the D matrix? The order of the D matrix is, of course, is 3 by 3, right? And we'll come to know what it is. We'll come to know what it is. But in 2 dimension, we have two cases. In 2 dimension, we have two special cases. We have two cases which are we can call them as two special cases. Okay. For simply, if it is 1 dimension, you have sigma is equal to E epsilon, or sigma x is equal to E into epsilon x, where E is a simple value. And of course, sigma is a simple value and epsilon is also a simple value. But in two dimensions, you have two special cases. One is plane stress and plane strain, and we define this according to loading. According to loading, we can consider them as plane stress and plane strain. Okay. So first one is plane stress. So let us see what exactly is plane stress is. Plane stress. A thin planar body subjected to, just a second. Okay, fine. So a thin planar body subjected to in-plane loading as shown in figure. I'll draw the figure so that you can see clearly. As shown in figure, is subjected to in-plane loading as shown in figure on its edge surface, on its see again I got some problem, just a moment. Okay, on its edge surface is said to be in plane stress. So it is very clear, a thin planar body, it should have only a simple plane. A thin planar body subjected to in-plane loading, the loading should be on the plane, in plane, subjected to in-plane loading as shown in figure on its edge surface. So it should be on the plane, but the loading should be on the surface, edge surface. Okay, is said to be in plane stress. Is said to be in plane stress. Fine. What is the example of this? I can give you an example as a ring press fitted on a shaft. A ring press fitted on a shaft. Here stresses sigma z, tau xz, tau yz are set to 0. Here stresses sigma z, tau xz and tau yz are set to 0. Okay, so what is this said? You can divide a two-dimensional object according to its loading into two forms. One is plane stress and the other one is plane strain according to the loading, right? The first one is plane stress, and what kind of loading it should be? The loading should be in plane. A thin plane, the thickness should be very small. A thin planar body, it should have only simple plane. It should be subjected to in plane loading. The loading should be acting on the plane, on its edge surface, and then it is said to be the particular object for that particular loading will be said to be in plane stress. Example is ring press fitted on a shaft. Ring press fitted on a shaft. So you have a shaft like this. Let us, for example, okay, let us suppose you have, a ring press. Okay, the loading is in this way. The loading is in this way. Right? Let us say the loading is P. Okay, so this is the loading I'm talking about, which is P. Okay, this is a thickness. This is a thickness. Okay, so this is my Z axis. So in the Z direction, the thickness is very, very small. You see, let us consider this as my X and this as my Y, and of course this is Z. But in the Z direction, I'm saying the thickness is very, very small. This is the side view of this particular ring press. And let us suppose there is a shaft inside like this. There is a shaft inside like this, and this is my Z axis, and I have shown here in this way. Okay, so this ring, this on the shaft, this ring is fitted. Why the ring is generally fitted? To provide the support, rings will be fitted on the shaft. Okay, for this, how the loading would be, wherever on the shaft, at whatever the place this particular ring press is fitted on the shaft. For example, you can imagine this like a bangle, or the kind of uh, that people Punjabis wore. Punjabis will generally wear. What is that? What we call kadiyam or something like that. Okay, so or you take a bangle. Okay, where the load acting on that particular bangle, if you consider this as a thickness of the bangle, then if you consider this as a hand instead of shaft, you imagine your hand. So where the loading is acting, where the contact is, on the shaft, where this particular press is fitted, then only at that particular contact place you will be having loading. And I said the thickness is very, very small. Okay, so the only on this XY plane the load will be acting, because I told you that the thickness is very, very small, so I do not consider, there is no load actually acting in Z direction. So sigma Z I can equate it to 0. If there is no normal stress in Z direction, there will not be shear stresses in Z direction. That means tau XZ, tau YZ should be equal to 0. Is that clear what I'm saying? Right? There is no shear stress, there is no load acting in Z direction. The load only is in that particular plane, in that XY plane. This is Z direction. The shaft length direction is Z direction. But the Z direction thickness is very, very, very small. So there is no loading actually acting in Z direction. I can, when compared to this XY, since the thickness is very, very small, I can neglect that loading in Z direction. So sigma Z is set to 0. If there is no loading in Z direction, if there is no normal stress acting in Z direction, then there will not be shear stresses in Z direction. That means tau XZ and tau YZ should also be zeros. Okay. Now, can I ask you what is epsilon Z? What is strain in Z direction? Can I simply equate it to 0? No. Even though there is no loading in Z direction, because the loading in XY plane, because the stress acting in X and Y directions, because you have sigma X and sigma Y, and you also have tau xy, the loading, because you have say, sigma x, sigma y. Obviously there will be shear stress in this xy plane, right? So because of this there will be strain in z direction, and the thickness is very very small. Whatever the small change in dimension, you cannot neglect it, because the thickness is very very small. One second. Okay, fine. So you cannot actually consider epsilon z to be 0. Why? Because of this loading. In the previous class we were talking about that. Because even though there is no, even though we didn't apply this, we applied stress in only in x direction, there will be strains. Strain will be developed in x direction as well as in y and z. One second. Okay, so that is the reason you cannot equate epsilon z to 0. You cannot say that there is no strain in z direction, because strain is change in length in that particular direction, and because of this strains in x and y direction, obviously you might have strain in z direction also, the lateral direction also. So you cannot simply equate it to 0. That is what I'm talking about. In the previous class, so in the previous class we have seen that when we apply stress in x direction, there will be strain in x direction as well as there will be strain in lateral directions in both in y and z. Similarly, even though we are applying stress only in xy plane, there will be strain developed. Of course, there will be strains developed in in x and y directions, but at the same time, there will be strain developed even in z direction. So you cannot simply equate z to 0. Okay. Fine. Okay, example is one second. So your example would be your you can think of a washer. You know washers, right? The thickness is very very small, but we put washer inside that that screw or something. Then the plane, if you consider this as washer, similarly same like this, if you consider this as washer, thickness, of course this thickness, the z direction, this z direction thickness is very very small, but the loading is on the plane, in this particular plane xy, right? So we consider these kind of problems as plane stress. And in math, understand very clearly that this is 3D. You have both x, y, and z. But because of this loadings only in, because we are considering loading in only only two directions, but we are neglecting the loading in other direction. We are, because of this loading, I should say, because of this loading, we are converting this 3D problem to 2D, and that is the reason I told you these are special cases. So no, in fact no object in this world will be only 2D. Whatever the small thickness would be, it will be having certain thickness, so it should be considered as 3D. But in order for our convenience, if you want to convert that to 2D, then there are two cases. One is plane stress and the other one is plane strain. Okay, so in the previous class we have considered the stress strain relations, and what is that? Epsilon x is equal to sigma x by E minus nu sigma y by E, or if it is three dimension, for three dimension what we got? Minus nu sigma z by E. But you know here we equated sigma z to 0, so you do not get this term. Similarly, epsilon y is equal to sigma y by E minus nu sigma x by E minus nu sigma z by E. Again sigma z is not there, sigma z is equated to 0. Gamma xy is tau xy by g. What is g? G is equal to E by 2 into 1 plus nu. What is 1 by g? 2 into 1 plus nu by E. So I can simply write 2 into 1 plus nu by E into tau xy. Am I right? Okay. So I got epsilon x, epsilon y, gamma xy, and I got sigma x, sigma y, and tau xy. Right? Now, so if I write epsilon x is equal to sigma x by E minus nu sigma y by E. Similarly, epsilon y is equal to minus nu sigma x by E plus sigma y by E. Same thing, but I wrote the x term first and then the second term, y term. Okay. Now, what is gamma xy? Gamma xy is 2 into 1 plus nu by E into tau xy. This one. Gamma xy is 2 into 1 plus nu by E into tau xy. Right? So if I write in a matrix form, because you know in 2D, in 2D we have sigma x, two normal strains, that is two normal stresses, that is sigma x and sigma y, and one shear stress. So sigma x, sigma y, and tau xy. Similarly, you will have strains would be two normal strains, epsilon x, epsilon y, and one shear strain, that is in the plane shear strain, gamma xy. Okay, so if I write in the matrix form, epsilon x, epsilon y, gamma xy is equal to some matrix. Some matrix, of course, for 2D we do know this is 3 by 1, and sigma x, sigma y, tau xy. This is 3 by 1. So obviously this should be 3 by 3. If I multiply these two, then I'll get 3 by 1. Right? So what this would be? What is in epsilon x? What is the coefficient of sigma x? 1 by E. In epsilon x, what is the coefficient of sigma y? Minus nu by E. In epsilon x, there is no tau xy term, so 0. Similarly, in epsilon y, what is the coefficient of sigma x? Minus nu by E. In epsilon y, what is the coefficient of sigma y? 1 by E. There is no tau xy in epsilon y, so 0. Next, in tau in gamma xy, there is no sigma x and sigma y, so 0, 0. What is the coefficient of tau xy in gamma xy? That is 2 into 1 plus nu by E. Right? But this is in the form, epsilon is equal to some matrix, let us say A, some matrix into sigma. Epsilon is 3 by 1, sigma is 3 by 1, and this matrix, let us say A, that is 3 by 3. But according to Hooke's law, I want this in the form, sigma is equal to some matrix into epsilon. Of course, man already let us say that is D matrix in 2 dimension. And we know sigma is 3 by 1, epsilon is also 3 by 1, right? This should be 3 by 3. How did we get this? In the previous class, we have seen that if I consider if I multiply with A inverse on the both sides, then A inverse into epsilon is equal to A inverse into A into sigma. A inverse into A is I. So I into sigma. If you multiply any matrix with its identity, appropriate identity matrix, then you'll get again the same matrix. So sigma. Therefore, sigma is equal to A inverse into A epsilon. So this A inverse is nothing but your constitutive matrix D. So if you find out this if you find out inverse of this particular matrix, if you find out the inverse of this particular matrix, then you get the D matrix for plane stress. Hope you guys understand what I'm saying. Then only you will get D matrix for plane stress, right? So we'll see this. We'll see this in the next class. Okay, we'll stop here now, and we'll see this matrix inversion in the next class. Is that clear? Thank you.